Hello, Precalculus students. This is a video to explain number 93 on your homework. The question was about an air navigation problem. It said there was a plane flying using air navigation bearings. It was at 148 degrees. With an airspeed of 875 kilometers per hour. That's this blue vector. So don't forget that air navigation, you're always measuring off of north. So when they say it's at 148 degrees, you're saying you always start rotating. You pretend that you're starting at the north position here, and you rotate clockwise 148 degrees. That's air navigation bearings. On the optional homework, a lot of you guys didn't quite get that problem right, forgetting that air navigation always states the bearing off of how many degrees off of north it is. And that is just how it's done. So that blue vector is the location of the plane. If it was flying with no other forces on it, no wind or anything, it'd be right there. But there is wind, so this other vector is saying, due to wind speed, it's actually traveling at 800 kilometers per mile at a bearing of an air navigation bearing of 140 degrees. Again, we're measuring that off of the north position, rotating here, and that says that this orange vector is showing where the plane's actually flying because of the wind speed. The problem is asking you to find the direction and strength of the wind. So we're going to do this, and it's going to end up being subtracting vectors to get the answer, but you'll see in a minute why, hopefully. There's our diagram. Over here, I named these vectors U and V. We're going to get the components that make those up, because when we combine them to get our missing force, we want to it's easy to do that in component form. So over here are my calculations to do U. Probably the hardest part of this problem is realizing you have to use negative 58 degrees instead of 148 for your angle here to get the components. Why is the big question. The reason is the trig functions, sine, cosine, and tangent, cotangent, secant, cosecant, they are all defined, and your calculator is expecting this, that you're always rotating angle where your starting side is starting at the positive x-axis and rotating. So even though air navigation gave us the angles starting at the basically the positive part of the y-axis, because that's the north position in north, south, east, west, and air navigation always starts there and tells you how many degrees off of north, rotating clockwise, that you want to travel in. You know, what direction are you traveling relative to north? The trig functions are based on angles where you assume your starting position is at as 0 degrees is at the positive x-axis. So we have to use angles that are the standard for trig functions, not air navigation. We know where our angle is from the given information, but starting here and rotating down to the blue, that is negative 58 degrees. It is not 148, and it's negative because in the trig world, I'm rotating negative 58. I could rotate positive 302 if I wanted there as well, and I would get the same answers. But it's easier to me to calculate negative 58. So this amount of rotation is negative 58 degrees. All I did was reason that there's 90 here. So I'm going to knock that off of 148, but then say, well, this remaining 58 has to be negative 58 to get here. If you use positive 58, you'd actually be taking the cosine of an angle up here, positive 58. And that's not what we want. So we're going to use negative 58 as our angle, because that in the trig world is the right location, the correct way to describe that blue location. And then doing the math, you get this vector for you that you can see here. We have to do the same thing with V, and the logic is same. We have to name an angle that in the trig world describes the location we're talking about. It's in the fourth quadrant. These two angles, they have to be fourth quadrant angles that we're using over here. So I use -50. Again, you could use +310 to get all the way to the orange position. You would get the same, any angle coterminal with this orange one would work, but -50 is an easy one to calculate for me. So you could use 310 though. Whichever you use, your answer is going to come out this. So here's the V vector in component form. So this is like your X, this is your Y. That also makes sense because there should be a -Y for these vectors because you're going out X, down Y to get to these endpoints. Okay. Now, the wind, I'm going to draw the wind in right now using, I use a color on this. Where are my markers? Well, I'll use this green. The wind speed you can think of as the thing that's pushing the plane to this new position, making it fly not quite at where you set the bearing. So you could set the bearing to fly at 148 degrees off of north, but if there's wind, it's not going to be where you're flying. Now, pilots and air navigation systems know about wind and how it's going to affect it, and you usually set your bearing to compensate for the wind. But anyway, this vector connecting these two other vectors, when you're trying to calculate that vector, it's usually a subtraction problem. Unlike the problem before this, in the with the two forces pulling on the same point, that's an addition problem. Now, the question is it U minus V or V minus U? And this is how I think of it. I'm going to put the same vector that I just did in green here up here with a starting point at the origin. So I'm going to draw it like that. And I think, how could I get to this endpoint using the two vectors I have? And one way to do it is to go out V and then back U. So I could go out V and then go back U plus V. This is if I go remember the direction, the positive or negative vector tells you if U is given as positive 875 this way, this is going negative 875. It's the subtraction of U to go this way. This is negative U. So I think of this as plus V. I went out V and then back U to get to this place. Because the wind is going that way. So I need to get to this place. If I did U minus V, I would be doing U and I would take V this way. And I would actually say, it would suggest that the wind is pushing that way, which it's not. So, oops, this is how I thought of it. The wind is pushing that way. That's why that direction on this vector has the arrow pointing toward the orange one. I slid that one down and thought, how do I get here? And it's out V, back U. So that's what I'm doing, V minus U. You have to think about it. Then, as we've learned, it's to do a subtraction of two vectors. You just subtract the component parts that match up. And you're going to get 50.4 and 129.2 as your two components. They asked for the wind speed. To get that, you will take the, that's the magnitude of this new vector, which is either here or here. And you do the magnitude calculation, you get 138.68. Our units on these vectors is kilometers per hour. That's our wind speed. Okay. Whoops. Sorry, I forget to move this. I'm still don't have a perfect system at home. My phone is resting on a stack of boxes right now. It's very jury-rigged. Okay, that's the wind speed. They also asked for the angle or the direction of the wind. So we're looking for this angle here or up here, this angle right here. But if you did a horizontal, I just did it separately. If I have a W like that, this is the angle theta we're looking for. We already found its magnitude is 138. So Tangent, you actually could use any of them once you get the magnitude, but you always have the two components are always x and y. So tangent theta is the y component, which is the second one, over the x component, the first. We're going to do inverse tangent, and we're going to write inverse tangent in front of our ratio. And you pull this up. And if you put that in your calculator, you're going to get 68.7 degrees. Now you might say, why isn't that the answer? It's because wind speeds are not given that way. 68.7 that's off a trig. That's rotation off of the positive x-axis to here. So, whoops, that's going, sorry, keep blocking the view. 68.7 is positive rotation from the x-axis up to where I have my w vector. But winds are usually given in standard bearings, which is using the north and the east, or the south and the west, not air navigation. Air navigation is specifically for just what it sounds like, planes and other things flying in the air. So just as you guys might remember, I'm not going to spend too much time on this because we did it back in, I don't know, chapter 4 or some, maybe 5, I can't remember what chapter. The regular bearings are given off of north or south. Since our vector is pointing up, this is pointing in the northward direction, it's not pointing down. It is a north, and then this number is how many degrees off of north. So if this was 68.7 degrees, that means this one is 21.3 degrees to make up the full 90. It's 21.3 degrees off of north. And which way is it off? Because it could go that way off of north, or it could go that way off of north. It's in the eastward direction. So that's telling me it's going that way off of north, not that way off of north. So that's it. That's the wind direction. And you might, when you hear the news tell you the weather, and they say you've got a northeast wind. Well, actually you have to understand a little bit more about it, but they tell you both north and east. That tells you in your mind, you think, oh, it's heading in the northeast direction, versus a northwest wind would be something different. Now, if it's coming out of the northwest, that's different than going toward the northwest. But anyway, there's more to it than that. But that is the wind direction, and that's how you should give an answer for a problem like that. I hope that was helpful. That was kind of long.